Hi. Okay. So, hey guys, we are back to calculus. And which number lecture is this?
Six.
Six. Okay. So, um,
Remember? Okay.
so, um, last time I've shown you an example which I didn't calculate, but the point was that you are not allowed to neglect things you think are negligible, because sometimes they are not as negligible as you might think. In this case, when we neglect one on the top function, yes, the square root of n squared is n minus n is 0. It's actually the limit. But here, if we neglect both n plus 1, because they are so small versus n squared, we will get also 0, but the actual limit is half. And I didn't prove to you why is the limit here half and why is the limit here 0. I will do that now. And in general, the two sides of the class, I said, we define limits and prove theorems, right? That's one direction. And the other is doing calculation, which is much more algebraic, arithmetic, and so forth. But we do use the theorems once we calculate, sometimes even without thinking about it, because a lot of the theorems are so intuitive, okay? So I'll show you this calculation, and then we will be back on our main course of proving theorems, using the definition, and understanding limits better. So class 6 and class 6, and we will start with calculating the examples from last session. So first of all, we had the square root of n squared plus 1 minus n. In general, I have a rule which is called WIN. It's a shorthand for wouldn't it be nice? And don't ask me why it's not WIBN. It's from obvious reasons, for obvious reasons. So wouldn't it be nice? I think it's such a vast principle across not only mathematics, in life as well, but we'll stay with mathematics, and you will get it after we'll do it a bunch of times. But for now, we'll hint at it. Wouldn't it be nice that the principle is that we think to ourselves, it would have been nice if it was this equation, because it would have been easier. And then we write what we would like, and then we cancel it out, so it's actually equal to what we have. Okay, that's the main idea. So here, what bothers us? What are you doing, the robot? Yeah.
There.
Okay. What is most what bothers us most about this? What would you like to get rid of? The square roots. How could we get rid of the square roots? What? Yeah, no, it's not that much of a win. Wouldn't it be nice if I was in Thailand? And then I say, no, we need to. So we want it to be squared, right? What operation could square the square root?
Square.
No. Why? Because if we square the whole thing,
Oh, you're still gonna
you
get
square this, we square this, and you get the multiplication. So you don't.
Oh,
You want to square this and square this, right?
it's operation as outside.
That does it make and you don't have.
Oh, I know.
Yeah, but this is so specific. It's okay if you don't guess it, right? You see it once, but I'm showing you this
Oh.
way of thinking because you will see that along the class, after a while, you will start saying so yourself. You say, what if this was here? What if this was here? And you will be able to. But here it's not that intuitive at all. Yes, Tomasi was first. Yeah.
Multiply by the square root of n2 plus 1 plus n.
Yeah, I multiply by the addition of these two. Why? Because a minus b times a plus b squares them both. Agreed? So that's exactly what we do. So we take what we had, we multiply, but by what we want. That's the wouldn't it be nice part. And it wasn't completely clear that that is what we would like. But from now on forward, you will have it in your toolbox as some algebraic tool that is very helpful to get rid of square roots. But obviously, there is no equality here, right? Agreed? So how can we fix that?
By dividing.
Dividing on the very same thing, exactly. That's the first time. And sometimes we add and subtract. Sometimes we square and take the square root. Okay, here it wouldn't help us, but that's the point. Yes. That's a good question, and I tell you why not. Because we're dealing with limits, and limits are not affected by a finite amount of elements. So we don't really care about that in limits, but yes. We use equality in calculus a bit loosely. It's not always equal, but it's equal enough. Yes.
I wasn't here when you did the win bit. What was that?
Wouldn't it be nice? So it's the way of thinking that what would I like to have here?
Like kind of forcing it.
Yeah. And like I said, we do it a lot in programming as well. Think, wouldn't it be nice if there was a function that find the midpoint? Then okay, I'll write a function that find the midpoint. That's the way we think.
Yeah.
That's the way you take a big problem and correct.
You tear it apart or yeah, break it down.
Break it down, yeah, thank you. Break it down to small problems. That's one thing. It's one element. And the other is just saying that is the way I want things to look at, like the design, and start to fill in the blanks. Okay? So we use it a lot in mathematics specifically. Okay, so now we do a bit of algebra, and above we have a squared minus b squared, which is n squared plus 1 minus n squared, right? And the denominator stays the same. By the way, I was mistaken here. That's plus. Okay. And the denominators stay the same. That's another reason it's not 0, by the way. I should have noticed by your question, but I didn't. Okay. So that's what we have in the denominator. What happened in the numerator? What do we have in the denominator here? And now I can ask about the limit. And what happens? The numerator is 1. The denominator tends to infinity, right? And we have a theorem for that. And you didn't really need to know that it's a theorem in this case. After a while, the theorems become more elaborated and convoluted and not intuitive. But we proved that 1 over a sequence that goes to infinity is a sequence that goes to 0. And that's the proof. That's a test level answer for such a question. It's a rather easy question, but sometimes it's a part of a larger one. If we study some function, we want to find the asymptotes, we'll find limits. So that is it in the test, no epsilon, no.
How can we be sure that the denominator tends to 0? I mean, it tends to.
Bit. And this turns to infinity because infinity squares tend to infinity, and the square root of infinity is infinity. These are all arithmetic limits, arithmetics that we will speak about later. We will not even mention them all because most of them are intuitive, but it's a part of a series of a sequence, a series of theorems, a series of the mathematical term sequences. It's a part of a set of theorems that we will learn about in the future. But you're correct now that I didn't prove it, but by the test it will be obvious. Yes.
My question may be a bit superfluous, but like if instead of n squared plus 1, like let's sort of it would be minus n, would it be the opposite of the original? So it would tend to infinity?
If we,
Another question.
I'm not supposed to. The problem means that I made a mistake. I'm not supposed to go there.
Yeah.
That would be in the original equation.
Yeah, in the original equation, that if you're asking where does this tend to, that's the entire question, right? And so that's what we're solving.
Yeah, just the inverse of the original would tend to.
What's the denominator?
No, it's 1 over 0. And like I said, we need to measure the sign to see if it's infinity or negative infinity. Here it's quite easy because obviously square root of n squared plus 1 is larger than n. Because if we strike out the 1, we get n.
And that's the reason why we have the second that didn't.
Yeah.
That's the reason why, because in the numerator it doesn't cancel.
Yeah, we'll do it now. We'll do it now. And we'll not just see why it's not 0, we will see why it is half, indeed half. Okay, so the next example is this. And the start is the same win. We multiply and divide by the conjugate, like the complex conjugate. Or let's write down everything all together. So we have this times this. What?
The spider.
The spider.
It's the TA.
Yeah. It's not understanding less than you guys. Okay.
I agree.
Okay. And here, agreed?
Okay, yeah.
So then I continue to develop the numerator. We get n squared plus n plus 1 minus n squared. The denominator is the same. And we get eventually n plus 1 over the denominator. So here,
Clearly one half.
Can't you see the half here? Yes. The numerator tends to infinity and the denominator tends to infinity. And that's a problem. We do not have a theorem, general theorem about this case. Infinity over infinity, because it depends on how large in the infinity is the infinity in the numerator, whether in comparison to how large the infinity in the denominator, excuse me. So we need to do something. And what we do next is we take out as a common factor the most affecting the most משפיע ביותר. Oh,
I mean, you mean the biggest possible, or
yes, the biggest element. I think it's fine. Significant, yeah, thank you. I keep losing words. I take out the significant element as a common factor, and I do it quite slowly. I do not neglect anything. Why? Because neglecting got me to the wrong answer of 0 from the start. So we don't neglect, but we take out common factor, the significant element. So in the numerator, who is the significant element? N. So I take out n. Under the square root, the significant element is n squared. So it's n squared times 1 plus 1 over n plus 1 over n squared. And here it's n. And then slowly, I take the significant elements outside. So here it's just outside of the square root. So if I take n squared out, what will come out here?
multiply by n?
N. And that's because n is positive. If it was x, I would take out the absolute value. We'll get to it when we get to it. And what happens next?
You add n on
All of the n's are canceled out, and we and we are left with 1 over 1 plus over 1 plus 1 over n over the square root plus 1. What? You said that our only agenda is to confuse you? It's just a minor agenda.
Ah, okay. Wait.
That's what I meant. Yes. But it actually solved the problem. Look why. The numerator, what does it tend to? 1. This
Bigger than 1.
1. It tends to 1. Right? 1 over infinity is 0. 1 over infinity is 0. 1 plus 0 plus 0 is 1. So what do we get altogether?
Honors.
Maybe you do.
Sammy, what is the answer?
It's 2, oh, sorry, 1 over 2.
Yeah, Sammy is right. Half. Because this is 1 over 1 plus 1. Agreed?
Yeah,
You got confused by the simple part, by the
no,
way.
I
The
understood.
end was the simple
No,
part.
I understood what you meant. I look at this, and what I think is that the under the square root you have a 1 over n plus 1 squared minus 1 over n, and like I would want to take that out, but sure.
What?
Under the square root,
Yes.
you have a in parentheses 1 plus 1 over n squared minus 1 over n, because
It might be, but I have 1 plus 0 plus 0. Why
Yeah.
in the hell, sorry for the language, would I want to? We wish to simplify things, not to make them more complex.
Yeah.
Why did we? So I'll take what you asked, said, Thomas, and take it in a bit of another direction. Why did we start with all this horrible algebra? because when we just started the exercise, this goes to infinity, this goes to infinity, and infinity minus infinity is a problematic case. I don't have a theorem that tells me altogether what happens. That is why I started to simplify things. Okay, I want to get rid of the problem. Okay, so this is the technical phase of the course, right? No, and there are two phases of the course: the technical one and the proof one. And students hate the proof one and the technical one, but nevertheless, it's very important to distinguish between the two because there are two different abilities that you need to acquire. This is the easier one because okay, it's surprising the first time you see it, but still technical algebraic. It doesn't require the same amount of understanding the material as the proofs does. But in any case, I had a problem. I did some algebra until I eventually got rid of the problem. I always try to plug in n, substitute n. I say 1 over infinity. And after I plug it in, I see I have no problem. So I don't continue doing algebra just because I like it. I only do the algebra when I have a problematic case. That's the general thing, okay? And another question that no one asked, but I will ask in your name. So we multiplied and divided by the conjugate, and then we took out the significant factor, right? Why shouldn't we just take out the significant factor from the original expression? So let's just see what happens if we do that, if we are allowed. Because it's just algebra. Taking out the common factor is always allowed, right? Let's see what happens. What would have happened if we took out the significant factor from the original expression? Oops.
It works.
Oops. What did you say?
Something stupid.
Oh, okay. I always assume that, but sometimes it's something stupid that has to do something with the class. Okay, sorry. I don't know, foreigners like gentle reading. So I always thought that whether my teaching will translate to another country. I think I would be thrown out on the first day. How did you talk to the students? Okay.
In all honesty, they deserved it, so it's fine.
Yeah, that's the best defense. You go to, you are stupid, you deserve it. How dare you complain? Yes, that's
Your
Great.
Honor, the kid got what he deserved.
yeah. Okay. And it's good that they don't hear you on the microphone. And so, like I said, we take out the common significant factor from the under the square root. So we get the square root of n squared times 1 plus 1 over n plus 1 over n squared minus n. Okay. Now we take it out and we get n times the square root of
Oops, we can't cancel it out.
this. We can't cancel it out, but we can take it out as a common factor. But
Yeah.
you're right in a sense that that would be the problem, but it doesn't have to be the problem. The fact that it can cancel out. So it's not exactly,
No effect.
it's something, but it doesn't have to be the problem. You will see the problem in a second. It's part of the problem. So Like the song saying, I'm the problem, it's me. So let's look at what we got here. The n wasn't canceled out. Where does it tend to? We're always trying to substitute the
Zero.
n.
No, I mean,
Infinity, right?
no, I mean, yeah, n tends to infinity, so this is n times zero.
Wait, so this is goes to infinity. This goes to 1, minus 1 is 0. So we have infinity times 0. And what's infinity times 0? 1/2. A problem, exactly. So the problematic cases, we saw 3 of them just in this exercise. Infinity minus infinity, infinity over infinity, and infinity times 0. These are all problematic cases. Why? Because it's not actual 0. It's a sequence that tends to 0, which means small numbers. And this is not actual infinity. It's a sequence that tends to infinity, big numbers. And if I ask you, if I take a big number and multiply it by a small number, could you guess what the answer will be? Obviously, it depends on how big a number, how small a number, right? And that's exactly what we need to do. So what happened here is we made no mistake, but we also solved no question, right? We got to a problematic part and we didn't skip it and pass it. And in the former way, we did get to an expression which has no problem. 1 over 1 plus 1, which is half. Okay? So students always say, how can I know what is the right way, master? And the answer is, you can't. That's one of the things that is most annoying in a technical question in calculus, is that you are not sure what is the right way ahead of time, but you need to try different things. That's why you have to be very fluent in your abilities in order to be able to try different things. Be sure that you made no mistakes, right? Because if I would make small mistakes, as some students say, and a calculation error, if here I would write 2 instead of 1, it changes the solution entirely, because it would be, if here was 2, right? So the whole parenthesis is 1 minus 2, which is minus 1, times infinity is minus infinity, and here I solve the question like that. And I can't claim calculation error because it's a big error. You understand what I mean? So the more fluent you will be in the algebra, the less mistakes you will have, and the more time you will have to the more complex questions in the test, or any other question, whether they are complex or not. So that's the technical phase of the course again. I put it always for you to remember that it's not just the definition and the proof. You need to understand these things as well, but it's not just that. And I would even dare to say that it's more the test is more technical than theoretical, but both elements are there. Okay. By the way, that's the difference between more harder versions of courses than easier one. It's there are also easy technical questions, but usually it's how much of the test is technical, whether how much of the test is theoretical. And the theory, that's why calculus has such a bad name, because most students are not able to solve the theoretical question. And if solving the theoretical questions is a requirement to pass the exam, then most students do not pass the exam. That's what's happening, like, I don't know, Tel Aviv, Technion, and whatnot. It's not exam. It's kind of like ours, just more theoretical question than technical, and that's what the student. It's not just that, but it's important to see where we are and what are the different difficulties that we need to endure, and there is a connection. It's not strictly technical versus strictly theoretical. It's combined, and my tip is to try to understand the theoretical part as much as you can, and obviously doing exercises and go over the material and whatnot. Okay. So that was a small detour in order for you not to fall asleep in the class. And now we're going back to stating and proving theorems. Back to the theory, back to the future. Back to the theory. So, theorem. Given sequences and Bn and a number L, and a number L. One. This theorem has three claims. One. The sequence AN tends to the limit L if and only if the distance between AN and L tends to
0.
0. Agreed? I'm not asking you if you know the proof, right? But does it make sense? The elements of the sequence tends to 3 if the distance between the elements and the number 3, for instance, tends to 0. Make sense? 2. If AN and BN both tend to 0, then the sequence that is comprised of the sum of every pair of elements, I mean A1 plus B1, A2 plus B2, and so forth, where do you think this will tend?
Also 0.
Also 0. Like I said, the theorems are quite intuitive, but proving them it's not that easy. And 3, if AN tends to 0 and BN is bounded, then AN times BN tends to 0. And you will excuse me that I will switch the order between the two. I just remember that in the proof of the third, I used the second. I'm not sure, but whatever. Bounded. And why is it so important that Bn is bounded? We just saw that if An tends to 0 and Bn tends to infinity, the multiplication can go everywhere, even half, right? But if An tends to 0 and Bn could not be too large because it's bounded by some number, then the multiplication will definitely go to 0. Any questions so far? So we will prove all 3 of these claims using the definition of limits. Proof. For one, it's kind of a weird proof, and you will see why. AN tends to L by definition if for every epsilon there exists a K such that for all n larger than k, an minus L is smaller than epsilon. Do you agree about this claim? This is the very definition of a limit, and saying an goes to L is simply this theorem. We usually write words and not just in a discrete mathematics form. But for this proof, I think it's preferable. You'll see in a second why. What does it mean that an minus L goes to 0? By definition, if for every positive epsilon, there exists some k such that for all n larger than k, what happens? So now I need to take the distance between the sequence and the limit and say it's lesser than epsilon. So the sequence here is this expression. And what do we claim the limit here?
0.
0. So that's the definition. But what can you say about this expression? What does it equal to? Minus 0 is obviously stricken, right? And what happens if I take absolute value of an absolute value?
Nothing.
So it's simply that. Agreed? So the two propositions are equivalent. Right? The an tends to L is this logic pasuk. No, I forgot how to say pasuk. Logical. No, pasuk.
Ah,
Pasuk logi. No,
it's a argument.
I don't know. Let me look for it for a second. Must have a word which I forgot. We use it all the time. It's English. And that's why I don't remember. It's a sentence and it's confusing. Because in Hebrew, a sentence is a theorem. I think that's why I don't remember it. You see what I mean? In Hebrew, mishpat is what we call a theorem, which is a claim that is true. Now, a sentence, it's in mathematical logic, is such a claim that I'm not sure if it's true or not, but I want to say it's equivalent to this sentence. Okay, try to remember that because it's not confusing in English. In Hebrew, a theorem is a mishpat, and the sentence is pasuk. Okay, so a sentence. So this logical sentence and this logical sentence are equivalent because the inequality is the same. The expression here is equal to that expression. And that's why an tends to L if and only if an minus L absolute value tends to 0. And I will note the following specific but important fact or consequence. Definitely false. Consequence, yes. Consequence. Oh, I will remember it now. Like a sequence of cons. A consequence. If L equals 0, then we get that an tends to 0 if and only if the absolute value of an tends to 0. See, I just plugged in 0 into that theorem that we've proven. An tends to 0 if and only if an minus 0 tends to 0. So that is so important that many times if we're dealing with limits which are 0, we can add or remove the absolute values, and a lot of time it's algebraically
Efficient.
yeah, I want to say invaluable more than efficient. Yes, it's so important sometimes. It's silly, but it's so important because when you add absolute values, you make sure everything is positive, and it helps to work with inequalities. And removing absolute values sometimes simplifies the algebra. So it's very, very invaluable. Okay, but it's just a specific case of something larger that we use. We usually use it with 0, but we sometimes use it with general L. Okay. Now we wish to prove 2. An is bounded. Sorry. An tends to 0 and Bn is bounded, and we wish to prove that the multiplication tends to 0. So for 2, now 2, since Bn is bounded, we can write that the absolute value of Bn is always lesser than some m. Agreed? That's the bound. Now, we need to prove that An times Bn tends to 0. We will do so according to definition. Let there be epsilon let there be positive epsilon. We need to choose k such that for all n larger than k, it is true that the sequence An Bn minus the limit 0 is smaller than epsilon. Agreed? Like always, we develop the inequality, but here we won't single anything out. We won't extract anything because we don't have an extraction. But what will we do? So An Bn equals the absolute value of An times the absolute value of Bn. Do you agree? And by our data, what can I say next?
I mean, I was thinking, can we just define it like the epsilon for An, and then say that we can multiply it by the inverse of m, and we have it?
Something like that. So, but we'll say that this is smaller than An times m. Agreed? Right? Because Bn is bounded by m. And now we're doing another version of a win, because that's what we would like. We would like it to be smaller than epsilon. Agreed? That is not given. That's that is what we want. So we wish that An would be smaller than epsilon over m. Agreed? Can someone or something ensure me that an will indeed be smaller than epsilon over m? What is the data?
That all of the elements from Bn are smaller than m, so
That's one part of the data. Bn is bounded. What else? What is the data on an?
it tends to 0.
It's 10 to 0, so obviously it will be smaller than that by definition. Since an tends to 0, there exists some index k1, such that for all n after k1, it is true that an minus 0 is smaller than epsilon over m. Epsilon over m is some radius, positive radius of an area, and an must be in this area of 0 because an tends to 0, and it will be in every area of 0. It's just a matter of since when. So k1 is the point in time after which the sequence will be in this area. So take k to be k1, and we are finished with the proof of the second claim. We have the third one yet. Okay, green. And I know it's tedious and hard, but still I implore you to try to understand it, because each time you will understand it a bit more and a bit more if you try to understand it. And if you say, okay, this is not for me, you very quickly lose touch with the course, and that's not a good place to be. Okay. 4.3, sentence 3. So here we assume that an tends to 0 and bn tends to 0. We need to prove that an plus bn tends to 0 as well. Given a positive epsilon, we need to choose k such that for all n larger than k, what happens? What do we need to prove that happens?
What do we need to prove? I mean, can you say there's two epsilons?
What do we need to prove? Not what you think you can prove. By definition, I was given a radius of an area. We need to choose some index that after this index, what happens?
All the sum of all of them is that's 0 now.
We need to prove that. That's the definition of a limit, is that you take the sequence minus the limit smaller than epsilon. So we need to prove that an plus bn minus the limit is smaller than epsilon. The same form all of the time. That's what I mean. You need to listen and then and try to understand, and after a while you get it because it's always the same. Look at it. This is because that's what we need to prove. Just a second ago, we need to prove that. So this is what was written here. And if we in here, we wanted to prove that an minus L goes to 0. So this is what we've written here. It's always the same, it's always the definition. Okay, but the sequence changes and the limits changes. So what do we do here?
Have a couple of options.
I take this. This is all obviously equal to that. I lose the zero basically. What now?
You have the option that either one of, like either of them have different signs, which is not interesting.
Yeah, we don't go there. You're correct, but it could be that sometimes n is positive, sometimes n is negative. It's too horrible of
Yeah, no,
a
I mean
path.
it doesn't really matter because in the end that's smaller than either of them.
It's not true. It's not definitely smaller than either of them. Both of them are positive or the
No, no,
same
I mean
sign.
no, I mean if they have different signs.
So what we need here is kind of like what you're saying, the triangle inequality. Do you know it? Have you seen it?
I've heard of it, I don't remember.
I'll show you here. A plus B is always smaller or equal to the absolute value of A plus the absolute value of B. Does this seem familiar? If not, then now familiarize yourself with it because it's quite important. But that is the triangle inequality. Excuse me. Very useful. So basically what I say is that the absolute value of the sum is small or equal to the sum of the absolute value. Okay? What do we wish to happen? What do we need it to be smaller than? Epsilon. And now, how can I make it true? It's again kind of a win. I'll just write a question mark, but it's the same thing. I wish to do something that will make it into an epsilon. So in order for the sum to be smaller than epsilon, what does each of them need to be smaller than? Smaller than zero?
Sorry. Each of them needs to be for the.
Uh,
It has to be smaller than that. So.
If
Half of epsilon.
half of epsilon, perfect, exactly.
In there, can we just say that because A tends to zero? Wait.
Yes.
Because A tends to zero, then mod A tends to zero. Because B tends to zero, mod B tends to zero, and therefore it's going to be.
That's the theorem that's the theorem we're proving, right, Sammy? That's the actual theorem. If an and bn tends to zero, then the sum tends to zero. So you basically said because it's true, and we can finish it quickly. You see, that is exactly what we're proving.
I
The
approve.
very intuitive thing to say, but how do we actually prove that it is true?
I mean, half isn't always true. Like each of them have to be lower than half, not necessarily.
And they do have to be lower than half necessarily. Why? Because they tend to zero. They will be as small as I need them to be.
Okay.
Okay. So since an tends to zero, there exists such a k, call it k1, such that for all n after k1, an would be smaller than half epsilon. Try to concentrate for a second. That's important. That's one of the, we'll see in this exercise something we didn't see so far. So an at some point will be smaller than half of epsilon. Do you agree about that? And similarly, since Bn tends to zero, there exists K2 such that for all n larger than K2, Bn would be smaller than half of epsilon. Now, what is the problem that I asked you to concentrate? The reason, which is the reason I asked you to concentrate. We wish for both to be true. I need both an to be smaller than half of epsilon and bn to be smaller than half of epsilon in order for this to be half of epsilon plus half of epsilon, which is epsilon.
I'm getting a single case.
But they both happen on different times. This happens after K1 and and this happens after K2. So is there a point in time where both are true?
The max.
The maximum, exactly. For example, think that this happens after the 100th element, and this happens after the 1000 element. So after the 1000 element, both will be true, because this is true since 100 forward, and this is true from 1000 forward. The intersection is after 1000. Okay, so that's exactly what we do. It's the first time that we don't just choose K to be K1. So we choose K to be the maximum between K1 and K2. And then for all n larger than K, it is true that n is larger than both K1 and K2 because it's larger than the maximum between the two. And therefore, an plus bn would be smaller than half an epsilon plus half an epsilon, which is a whole epsilon, and Q, E, P. Any questions so far? Yes, Thomas.
Is there a reason why we did this when both tends to 0 and not just like any number, any non-infinite number?
So Thomas asked, why did you say that if a and bn goes to 0, the sum goes to 0? You could more generally say that if n goes to a and bn goes to b, the sum would go to a plus b. That is true. The thing is, that is my next theorem. I will prove that what I just said using the 0. So it's easier to prove around 0, and then I use it everywhere. That is actually my chidush. Usually in lectures skip this and just prove the general case. And I feel it's better to prove everything around 0 and then learn from it the general case. We'll see it in a few minutes. Yes.
Can you quickly go over the proof for number 1 again?
For number 1,
Yeah.
yes, I just wrote the definition. That's why it's so confusing. An equals to L if this sentence is true. Do you agree? Can you see that is the definition?
Yeah, definition. Yeah.
And an minus L, the sequence, the absolute value of an minus L goes to 0 if this sentence is true. That's also the definition, right? Because this is the sequence and this is the limit.
An minus L.
Yeah. An minus L absolute value. That is the sequence of number we're looking at. And I claim that it goes to 0. So I plugged it into the definition.
As in every n eventually will.
Yeah.
Okay.
And then I noticed that this expression within the two definitions is equal. Right? You get the very same logical sentence because this expression actually equals this expression, same value. So it's the same claim.
Wait, what have you equate? Oh, I see.
This, let's put it in the color, and this. Other than that, there is no difference whatsoever in the sentence, and
Right.
these two expressions are equal. So it's the same sentence. So this one's true if and only if this one is true. We're basically saying
You
the
said
exact same
because
thing.
on the left-hand side, not on the left. Because the statement
Because
that you
this is exactly the same.
right.
There's no difference here whatsoever. The only difference is supposedly this expression here. But it's not really a difference because it's equal.
But how can you say that those two? I kind of out. Just because they're smaller than epsilon doesn't mean that they're equal. Right?
No, it's equal. No, it's equal because it's equal. Minus 0 you can strike out, and double absolute value is the same as one absolute value. I'm algebraically proving that they are equal.
So why do we even need the definition then? Can't you, if you're proving it algebraically, can't you just say
I need to prove that the green claim is equivalent to the cyan claim. Okay? I need to prove that this is equivalent to this. The only way to prove that it's equivalent is to understand what does it even mean. So I have to go through the definition. What does it mean that AN tends to L? What it means is this mathematical sentence, logic sentence. We say that AN tends to L if and only if this sentence is true. By definition. Do you agree about that claim?
right? I agree. Oh wait, I'm being stupid.
And this sentence this claim just says this sentence. And what I'm saying is that both of these sentences are the same sentence, basically, because the only difference in expressions is one that equals to the other. So it's the same, they all simplify into the same claim.
Okay.
So now a theorem which I dedicate to Thomas. Given two sequences AN, BN, such that AN tends to a finite number L, and finite number A, and Bn tends to a finite number P, then AN plus BN tends to A plus P. We already used this theorem today. Why? Up here on the technical part, where did you say, excuse me, where did you say this sequence tend to? No, just what I selected. To 1. Why, Sammy?
It's 1 over n. Sorry, 1 tends to 1. 1 over n tends
Exactly.
to 0. 1.
Because this turns to 1, and this tends to 0, and this tends to 0. So the sum would be 1 plus 0 plus 0. That's the very theorem I'm stating now and wish to prove. So when I use it, I don't have to reprove it, but we need to understand the proofs at this simple stage, because later on the course and on Infi 2, Calculus 2, the claims will be much more complex. And then it will be hard to understand what I'm claiming and the proof. So now enjoy the fact that you're simply not understanding the proof, but at least we're understanding what we're claiming. Okay, can't say it enough. I just talked with someone who is in charge of teaching math in the computer science, and she told me that on one of the past semesters, one of the lecturers skimmed through this part and say, oh, it's not important. Actually, I felt it myself a year before, but doesn't matter. I did speak about it with a colleague. And then on calculus 2, it was horrible because the students didn't know how to understand the proof and they couldn't understand calculus 2, and I don't wish it to happen to you. Yes.
We need this in order to prove number 3, because otherwise, why can you do epsilon over 2 plus epsilon over 2?
This is just this is an is smaller than this number for all n. So this is just if one fixed number is smaller than another fixed number, then you can add the two, right? Here I want to talk about the limits. Epsilon over 2 is not the limit of an, it's a bound, okay? So the proof here would be quite easy. Why? We don't even mention epsilon. And why is that? Because we use the previous theorem, okay? We know by the previous theorem, an plus bn tends to a plus b if and only if the distance between them where does it tends to? Finish the sentence and ask again. an plus bn tends to a plus b if and only if the distance tends to 0. So that is what I need to prove. Okay, that is what I need to prove. Now look, we have an plus bn minus a plus b. Wouldn't it be nice? Can anyone guess what would be nice here?
We just did an minus a and bn minus b.
Yeah, that's an minus a plus bn minus b. And it's nice because it's actually true. It's equal. Do you agree?
Mhm.
Where does this tends to?
0.
Why? Because an tends to a. So this tends to 0. Where does this tends to?
0.
Right. And what can you say about the sum of two sequences that tends to 0? Tends to 0 again from the previous theorem. So we proved everything around 0 using epsilon, giving us the ability to move past it. So a lot of times we will try to move past epsilon proofs, but it will always come back every now and again, more scarcely as we move along, but still it always comes back, even in calculus 2. Okay, so we've proven that on addition, excuse me. Now I wish to prove it about multiplication. Theorem. Assume an tends to a finite number a and bn tends to a finite number b.
What do you mean by finite number?
Rather than infinity. I could write number, but I want to no, it's not pedantic, it's להדגיש, to emphasize. that it's not infinity.
No, I was just thinking, because technically there's some numbers and real numbers that aren't finite numbers.
No, they aren't. They
They
aren't.
don't.
All numbers are finite. Every number is finite.
You mean not rational?
Yeah.
You mean they have infinite number of digits, but it's still a finite number. Square root of 2 is a finite number, right?
Okay, okay.
It's smaller than 2. So that's pretty bounded. Okay. Uh, but again, I just wish to emphasize a number and not infinity. Because for infinity also, this theorem don't make sense even. What is infinity plus 5? Okay. And so assume an goes to A and Bn goes to B. And then an if the WhatsApp alone, an times Bn goes to A times B. Does that make sense, first of all?
Yeah,
Now the question is, how do we prove it?
with pain and suffering. I mean,
While pain and suffering, but not using pain and suffering. It's not enough.
I mean, having that it tends to A, if we use the formula that is an minus L is less than epsilon, we can say that the difference with AB is 0, and that's it. No,
It's not 0, it's more than epsilon, it's different than 0. If you think about it, it's actually an algebraically not clear claim. I'm saying that if an is very close to 3 and bn is very close to 4, then their multiplication is close to 12. Not completely clear why. Think of it as an as being 3 plus some error and bnb 4 plus error. If you multiply it and do distribution law, you get an times the error and bn times the error and the error squared. You get something which is a bit more complicated. It is true, but it's not. I wouldn't say it's obvious. Yes, Sonny.
You do the, wait, is this exactly what Tom said? You start the same way that we did above, where we do the an plus bn minus ab tends to 0.
That's true. We need to prove that a and bn minus ab tends to 0. That's the very first step, the grid. And now what?
And then we have our second rule, which was about if one thing tends to 0 and the other thing.
But none of the things
yeah.
here tend to 0. That's the
Mm.
problem. A tends to A, Bn tends to B.
you can take out the distributive, right? It would be too easy.
What do you mean?
Just do AB times approximately.
What's approximately?
Yeah, exactly.
Times approximately.
Mm,
And neglect, and that's it, finally.
Oh, right.
Using the easy to see rule. Yes, yes.
Can we write an and bn as like brackets, like an in a bracket times bn in a bracket? And we say that an, because an tends to a, we can, like what Tom said, we can just factorize it out.
no,
No?
because it can be coming from whatever direction, so you don't know the limits.
Which means whatever direction.
Like it can, like AB can be coming from a infinity, not infinity, but some, yeah, some infinity and going into AB.
Thomas,
So it's
Wouldn't it be nice? You wish to factor out something, and currently you cannot factor out anything because they don't have a common factor. Agreed? So what would have been better? If should have been
ANBN,
what?
ANBN.
No, that yes, yeah, that's true.
That's too nice.
No, but no, yeah. What something in between, something that cancels completely out, and what we have. Can you guess what would I like here?
I mean, apart from 0, that takes-
Yeah, you don't like 0, no. You want a common factor, right?
Mm.
swap this with something that has a common factor with A and Bn. What? A. No, but that's too much, right? Because A and Bn minus A and Bn. It cancels out.
A and Bn squared?
No,
ambient of it two,
no.
ambient times two.
1 over A and Bn.
Log n ambient.
A and B, A and B. Small steps, small steps. One of them is equal, the other is just approaching. So, is that equal to what we had before? No, so we need to fix that. Add A and B,
Yeah.
and what are we left with? What do we need to add?
Minus
Minus AB. Do you agree that this equals what we had in start, right?
Yeah.
That is nice. That is nice. Why is that nice?
Oh, because we can factorize
AN times
the BN.
the first from the first pair,
Oh wait.
from the first pair,
Times
BN.
yeah.
BN minus B. And for the second pair, AN minus A. So this tends to 0, right? What do you know about the AN?
That's 2A.
Yeah, but that's not helpful.
Oh, it's bounded
Why is it bounded?
because it has a limit that is infinity.
Exactly. We learned the theorem last session. We proved it actually. That I'll write it as a note. Note. AN is bounded since it has a finite limit. That's a theorem we learned. Okay. And that's another reason you should try to understand the proofs, because we try to understand the proof, we remember the theorem, and it's easier for us to use it.
Oh.
And B is a finite number, so it's obviously bounded. And this turns to 0. So we have bounded times 0, which is 0, plus bounded plus times 0, which is 0. So it's 0 plus 0, which is 0, basically. Okay. So the whole genius part here was to move everything to 0, prove the hard stuff there, and then just leave the wouldn't it be nice cities to prove here.
This is disgusting.
And let's just see how Wikipedia proves it. Arithmetic of limits. This is beautiful, not discussed. Let's see if the proofs are here.
The amount of make-believe necessary to achieve a proof is impressive. I chose a degree that wasn't art because I'm not creative, and now we have this.
Math is art. Pure science.
The art of computer science, the art of computer programming. Yeah.
Oh, it's limits, not arithmetics. Oof.
Sum of limits.
Out of limits.
Let's see if this is in English. I scroll down and I didn't even read. Oh, it's not in English. Okay. So the proofs. Oh, they proved it on the function. It's about the same. It's about the same. They show it a bit differently. They say, what is fg minus ab? Say f minus a times g minus b, which is 0 times 0, right? Wouldn't it be nice? Because it's not what we have. And what do they suppress? whatever is subtract, whatever is remains. So it's not exactly what I did, but it's the same idea. Okay. I've never seen it written in this way, but I don't know. It also makes sense as a wouldn't it be nice? And eventually we get to the same thing. 0 times 0 plus 0 bounded plus 0 times bounded. It's the same. It's equivalent. Okay. Any questions thus far? So, let me just think. I don't wish to completely kill you at this point. I've proven these two out of the arithmetic. And why is it called arithmetics of limits? Because we do arithmetic on the sequences, and we wish to know if the same arithmetic hold for the limits as well. Okay, and sometimes yes, sometimes no. I will write the next theorem and won't prove it. Theorem without proof. I'll write it as an exercise. Exercise. No, it's not. Exercise. If an tends to a number, and bn tends to b a number such that b is not 0, then an over bn tends to a over b. Make sense? Another theorem where it's not even an exercise because it's quite hard. We don't do it in the lectures because it will take us, I don't know, like a couple of lectures to prove it. In the Math Wiki, there is it's broken down into a few smaller exercises for whoever wish to follow it. But another theorem is if an tends to a number a such that it's more than square root, such that a is positive and bn tends to b, then an in the power of bn tends to a in the power of b. So that's also arithmetic, but of powers. But that is more complex, and I won't prove it. But you can use it. And Thomas, you mentioned the square root. Square root is the power of half. So it's a specific case of this general theorem, which we use, but we don't prove it because it takes too much time. Here in the Math Wiki, I'll just show you. Where is it? Here. So it's broken down, like I said, for a few exercises with the ideas behind them. You're welcome to try to read it. You don't have to. It's not important, right? Not because it's too hard, because it's too long obsessing about these rules when there are far more important things. Okay, so now, like I said, I don't wish to do any large proofs now because your mind has turned into jello. I wish to show you something which is both interesting and constructive, relevant, right? Not just something interesting, right? Kind of something that has to do with calculus. So I think I've shown you Euclid elements before, right? Okay, but I will show you a certain proposition here, which is quite nice. If from the greater of two unequal magnitudes. So we have two positive numbers. One of them is greater than the other. Agreed so far? Laid out. A part greater than half is subtracted. So from the greater one, I have two numbers. I take the big number and cut it by half. Okay? Will it be smaller than the small one? Not necessarily, right? Could be much larger. But I take half. And the remainder is greater than half. Then I do it right? I lost my train of thought. From the greater of the two unequal magnitude laid out, greater than half is subtracted, and from the remainder, a greater than half is subtracted, and then you do it over and over. Okay, you take out half, and then out you take out half of what you had, and half of half, and half of half of half. Eventually, what will happen? Eventually tends to zero is a false sentence, you know, because tends to zero is the entire process. What happens in eventually? So let's think about it in the and again, I just wish to remind you this is 300 BC, right? So think about cakes. We have a whole cake and I have some slice. Okay, so I get the slice and say my brother, I don't have a brother, but my brother have a whole cake and I'm jealous and I go to my mom and say, oh, he got a bigger piece than me. So my mom has the whole cake and still his piece is bigger than mine, right? So I continue crying. Then mom again slices a half and over. What will happen eventually? His piece will be smaller than mine. Agreed? My piece is the epsilon, which in modern terms we use. It's some magnitude. That's what he used. He used the smaller piece to be like the epsilon, some arbitrary small piece. And then he say, if we have half the cut in half over and over, it will be smaller than epsilon. That is the definition of tending to zero. So what he's claiming here, that's a theorem, that's one over 2 to the power of n, that's half time half time half time half tends to zero. So that's the way Euclid proved that. That is one of the things we will need to prove. We'll prove it in another way, but Euclid proved it this way. And I wish to quickly go over his proof because it's quite nice. Say the larger magnitude, the larger number is AB, okay? And the smaller number is this segment here, C. So what it said multiply the smaller segment enough times until it passes the larger one. That's just division. You divide AB by C, some integer number of times, it passes AB. Agreed? Now, assume here there are more than two pieces, at least two pieces, but more than two pieces. If you take out a half of AB and you take out the last segment here, obviously you took out more than this piece than this one, because here you took a half and here you took less than a half, because this magnitude repeated at least 2 times, even more. And then you take out a half of this, and then another segment here. And again, a half of this is more than what you take here, because if it's not smaller yet, then a half of this is more than what you take of this, because this is less than half. Until the first time, in the drawing, it's a bit confusing because after the first time is already smaller, right? But you need to imagine that after the first time, this is still bigger, and half of this will be more than one more segment. And after enough times, sometime this will be smaller than what you have here, which is a couple of segments. And then when you do it until you get to the last segment, excuse me, and then this will obviously be smaller. And that's the Euclid proof. We don't need Euclid proof because we will prove it in the modern terms, but actually Euclid's proof is quite nice. And more importantly, it's so old, and this is calculus, and that's why it's so hard. We really learn human knowledge that human scientists versus AI, but scientists have used throughout the years to go forward. They all started with this, and then they build on top of it, and now you're learning the start. Okay, so have a nice Passover, and I'll see you afterwards. Bye bye.